Dear friends, in this video we study the effect of the pressure losses in a plastic hose when water is flowing. We understand first the meaning of pressure loss, then we learn a mathematical formula and we see what it depends upon. And finally we assess the theory with experiment. Let's start. The first part of the video is introduction to the problem. Then we attempt a description by mathematical formulas. The theoretical results we assess during the trial phase. And finally we do our observations regarding if and how the theory and experiment match together. The problem we may describe in this way. We have a very simple hydraulic circuit consisting in an upper tank with a big volume, a lower tank or a canister with a smaller volume, and a hose in between. The difference in elevation we call h. Moreover, we call capital L the length of the pipe and capital D its diameter. The task of the experiment is to meter the time needed to fill the canister having a fixed volume. We repeat the experiment under different conditions, with a small hose, with a wider hose, with a longer hose, and with increased difference in height. We find a formula and we check with the experiment if the formula is describing the reality. The theory says that the hydraulic head within a circuit stays constant if there are no losses. The hydraulic head is a sum of three parts: the pressure, the geodetic and the kinetic part. The head losses, capital Y, has two parts instead. One is the distributed losses and one is the concentrated losses. Both are depending upon velocity square. The first is depending by means of a factor F into L divided by capital D. It means this is proportional to the length of the pipe and inversely to the pipe diameter, while the second is proportional to a factor K that is depending upon the geometry change of the pipe. In our case, besides the losses due to the pipe length, we have also the effect of the sudden diameter change when the water is entering the pipe from the big tank. Therefore, we write the energy conservation law from the point capital A to the point capital B, while the head at the point A has this expression, but since there is no velocity and no pressure in the tank, has only the geodetic part that we call H. The head at the point B has no geodetic part because we take this position at zero elevation for reference. It has also no pressure because the water leaves the pipe at atmospheric conditions and only remains the kinetic part. The energy conservation says that the head at point A equals the head at point B plus the head losses, capital Y, that we have expressed above. If you replace that expression, we find the relation at number 1, where the velocity at point B we have called v. If we work out this expression solving for v, we get the formula number 2. At the numerator we have the velocity when there is no friction. We call this quantity v0, while at the denominator we have a friction coefficient, capital Fc, that takes into consideration the losses, both the distributed and the concentrated ones. This coefficient we do not have to confuse with the friction factor F mentioned above, We will describe this factor in the next slide. The friction factor F is used only for the distributed losses. It is an experimental coefficient whose value is displayed in the chart aside. We can also express it by using an empiric formula. The formula says that F depends upon Reynolds number for laminar flows, also when Reynolds is less than 2300, and then it depends only upon the pipe roughness E and the diameter capital D of the pipe when the flow is turbulent for Reynolds greater than 2300. For each different material, according to its specific machining, we can define a roughness E. We can see in the table few examples. The friction factor is a pure number, it is dimensionless. For a plastic pipe, the typical E value is 0.0015 mm. So if you take, for example, capital D 8 mm, we get for the F a value of 0.014. The coefficient K for the concentrated loss introduced at slide 4 is also experimental and can be found from the table aside, the second column. In this case it turns into 0.5. If we consider a plastic hose having length 6 meter, diameter 8 mm and having a differential height of 2.65 meters, adopting the friction factor F found in the previous slide, the friction coefficient turns into 3.42. The speed when no friction, V0, is 7.21 meter per second, and the speed under friction is V0 divided by the friction coefficient, also 2.11 meter per second. The volumetric flow rate is the product of the velocity and the section of the pipe, its cross-sectional area, and turns into 0.106 liter per second. To find the filling time, we divide the volume of the canister by the flow rate. The canister volume is 5.3 liters, therefore the filling time is something about 50 seconds. We need now to confirm the theoretical results by means of the trials. As already introduced at slide number 3, we will run 4 different trials whose details are listed in the table aside. In the first trial, we use an 8 mm hose having a length of 6 meters. In the second one, a 12 mm hose with the same length. In the third trial, we adopt the same diameter but double length, 12 meters. And the fourth one, same diameter and length but a higher difference in height, almost the double. Moreover, we meter the exact volume of the small canister by using a scale. The net weight is 5.3 kg, also 5.3 liter is its volume. The task of the trial is to meter in each condition the filling time.
Good morning, dear friends. Today we are doing an hydraulic experiment using hoses. In the first experiment we are using a plastic hose having 8 mm diameter and 6 meter length, and we assess how much time does it take to fill a canister of 5 liters by getting water from a higher canister, much bigger, at a difference in height of 2.65 meters. The experiment number 2 is using the same length, also 6 meters, but a bigger diameter pipe. Instead of 8, we are using 12 millimeters. And the third experiment, the same thicker diameter, but double length. Instead of 6, 12 meters. The last experiment is using the long pipe, also the 12-meter length, 12 millimeter wide, but with a higher difference in height. Instead of 2.65, 5.5 meters. And in any experiment, we assess the time to fill the canister. And then we'll study what is the effect of the hydraulic resistance case by case.
This is the experiment number 1, and we start feeding the canister and metering the filling time. To make it shorter, we add some speed increase. In the middle of the video, it is 4 times the real speed. Now I switch back to the real speed and we meter 91 seconds, considering that we have a delay of 2 seconds while starting the recording. This is the second experiment with a bigger pipe size. Also in this case we increase the speed during the internal time and we switch back to the real time at the end of the filling. We meter 29 seconds. The third experiment with the double length 12 meters. The recording says 43 seconds. And finally, the fourth experiment with the increased differential high. We had to position the canister at the second floor of the house. We start the filling. Speed is increased 4 times. Then back to the normal speed and we meter 28 seconds. Some observations. The experiment number 1 does not match with the theory. The metered time, as we can see from the slide number 9, is 91 seconds, while the calculated time is 50 seconds, as we stated at slide number 6, by using a literature value for the roughness E of 0.0015 millimeters. The bad news is that all other experimental values are also not matching, being the calculated times always less by a deviation of 40–45%. What we are looking for is if it does exist a value of the roughness E so that experiment and theory are consistent, and we ask if this value of E is reasonable. We look for this value by using the least square method, and the result says 0.16 mm. In such a case, the error is always less than 6%. Question: is this found value reasonable? Actually, this is more than 100 times bigger as the one suggested by literature. However, similar values of the roughness can be found by other materials, for instance galvanized iron. As a conclusion, we can say that the result is realistic if we consider various irregularities of the hose geometry, for instance the not perfect round shape or the curves, that cannot be taken into consideration in the simplified model. What do we do with the results? We can find the flow rate capital Q from the quantities capital D, capital L, and H, also from the pipe geometry and from the differential high by using this formula. We remember that the flow rate is the product of the cross area and the velocity. This is formula number 3. Another way to proceed is to find the differential high needed to produce a certain flow rate with a given hose. And we can use the formula number 4. How to interpret those formulas? If there is no friction, also the friction coefficient is 1, the flow rate has a maximum value for a given differential high. The friction has the effect to reduce the high from the physical one, h, to an equivalent h prime that is practically the ratio between the physical high and the friction coefficient to the second power. The distributed losses are proportional to the ratio between the pipe length and its diameter to the fifth power. Now we want to see some extension of the application seen up to now. For instance, what happens if the length of the pipe is less than the required differential high? In such a case, the gravity is not enough to produce the desired flow rate. We need a mechanical pumping system. That's the reason why the same equations can be used also for a water pumping system, where H is the pump head, so this is not any longer a differential in the elevation, but is the mechanical head of the pump. The pump power in kilowatt we can express by using this formula, where the capital Q is the flow rate in liter per second, H is the head in meter, and eta the pump efficiency. What happens if we have a network with a pump as schematized in the picture, so two tanks connected with a pipe where a pump is used? In this case, there is no difference in high, and if there is no difference in high and no diameter change, then we can write the energy conservation in such a form where the head at the point A and the head at the point B we can express by the general formula with 3 contributions. But because there is no differential high and because there is no change diameter, it remains only the contribution due to the pressure. Therefore, the head loss capital Y is only given by the pressure change. That is the reason why in the technical language the head losses are also called pressure losses. And in the specific example, the pump head is given by this expression that we can obtain from the formulas already seen in the past slides. The presentation wanted to demonstrate the use of the formulas for the calculation of the water flow, knowing the head or vice versa, under consideration of the pressure losses, and we learned how they are built. In the examples, we have introduced a friction coefficient that takes into consideration both the distributed and the concentrated losses. For a more complex network, it is in general not possible to adopt an overall coefficient, but the procedure is similar. I hope you have enjoyed. See you next time. Bye bye.